Yeah, thank you, Davide, for the nice introduction. My name is David Erzmann. I'm a PhD student at the University of Bremen in Germany. And I will talk about the DL4TO library today. DL4TO stands for Deep Learning for Topology Optimization. And in order to talk about that specifically, deep learning for topology optimization, I need to first talk about the basics a bit. So I need to tell you, you probably don't know what topology optimization is. So I will first start with an introduction into what is topology optimization. And I will only then talk about deep learning methods for topology optimization, and later talk about my library and about some experiments that I conducted using this library. Okay, yeah, so let's start with this question: what is topology optimization? The goal of topology optimization is to optimize mechanical structures, often in two or three dimensions. What optimized means differs a bit on the application, but in general, optimized means that we want to build structures that are as light as possible, but also don't break under the applied forces. So usually the pipeline is like this, that we are given a certain problem or set of problems, and each problem contains some forces that we apply. It contains some homogeneous theoretically boundary conditions which signify where the structure should be locked in place. Like you can imagine, for example, here a screw sitting in the middle and holding everything kind of fixed in place there. And then we are given some information on the design space, which tells us where there are certain constraints where we are maybe not allowed to put material, or where we should definitely put material. For example, also here in the middle, right? We don't want to put any material there because there should be the screw later on. And then we are given some material properties, like, for example, the type of material that we are using. Usually this is some type of stainless steel or aluminum. So we know this material type in advance, and then we want to find an optimal material distribution. So what this refers to is we want to find a density function that is, where zeros indicate the absence of material and ones indicate the presence of material. So the way that mathematicians tackled this problem usually is via what is called compliance minimization. Compliance is, you can imagine this being a measure for the structural integrity of the structure. So minimizing the compliance means maximizing the structural integrity, so to say. And we want to minimize this compliance subject to the physics that should be fulfilled, some weight constraints, and that we have a binary density. So in mathematical terms, compliance is simply the scalar product between the forces that we apply and the displacements. And the displacements are what we get as a solution of the PDE. This is the PDE of linear elasticity. So we need to solve this PDE to get the displacements from which we can compute our objective function. And we have some volume constraint that we fix in advance, and we want a binary density. I will first talk a bit about a common classical approach that is most commonly used for this problem, which is called the SIMP method. And the SIMP method is basically in its core, if I simplify it a bit, it's basically in its core a gradient descent method. So it's an iterative approach where we start with an initial density, and then we calculate some objective or loss function, which is in this case, for example, a combination of the compliance and volume term. And then we perform gradient steps on that and optimize iteratively our density like that. And we perform some tricks, including application of such a function here of a smooth Heaviside function in order to promote binary densities. So we don't perform binary optimization directly because that's not easy. So we use continuous optimization, but use some tricks to promote binary densities and to enforce binary densities in a way. And then we repeat that over and over again. And the big problem with this classical SIMP method is that it is an iterative method, and in each iteration we need to solve the PDE for linear elasticity, right? Because in the compliance here we need the displacements U, which are the solution of the PDE. So we need to solve the PDE over and over again, which quickly becomes very expensive, especially if we are in 3 dimensions and if we are on high resolutions. So that's the main reason why people started using deep learning for topology optimization. And the whole field of topology optimization started in the 90s. And deep learning methods only recently started, with the first publication being in 2017. So this is quite a new field. And there are mainly 3 different approaches for deep learning in this field. The first one being that we simply learn the whole mapping from the problem formulation, so the set of forces, boundary conditions, and so on, pre-process that in some way, and then directly learn a mapping that outputs in an end-to-end matter the density distribution, the optimized one. We can do this either in an end-to-end way, or we can do this iteratively. And this is also the first approach that has been used, and I also made a publication on that, and I will talk about that a bit later. Second approach would be to learn a substitute for the PDE solver. And this is something that I'm currently working on, so I'm currently writing a paper on that. And the third approach is neural reparametrization, where you reparameterize the density mapping with a neural network, which you can evaluate at any point, and so you, in a sense, get an infinite resolution. The problem with these approaches is that most of them are data-driven, and you need a lot of data for that, usually. If I just take some quotes from the literature, you can see that they commonly take hundreds of thousands of samples. And what's even worse is that most of these papers are supervised because that works best. So these samples not only contain problems, but they also contain ground truths. So you kind of need to generate hundreds of thousands of ground truth densities using the classical method, and that takes a lot of time. And this is what makes deep learning in this field currently very difficult to use in real-world applications by engineers, because you can't expect an engineer to run the classical algorithms hundreds of thousands of times just to generate a data set. But this is not only a problem for the application side, but also for the research side, because currently there exists not a single public data set. So this means that not only each researcher has to generate his own data set on his own, but it also makes all the literature out there non-reproducible, because you don't have access to the data sets. So that's why basically the first thing that I did while working on this topic is I generated these data sets for topology optimization in cooperation with the Ariane group, who built space rockets, and the DLR, which is the German space agency, so basically the German NASA. And I published these 3-dimensional data sets online on Zenodo. So now I will talk a bit about my library. Because, again, DL4TO stands for Deep Learning for Topology Optimization. And this library is a Python library for 3-dimensional topology optimization. And the nice thing about it is that it is entirely based on PyTorch. So you can easily integrate deep learning into your models, into your topology optimization pipeline. Deep learning features are, for example, the SIMP method, which is the classical method that I showed you in the beginning. And it also comes with its inbuilt classical PDE solver. And you can generate, import, and export custom data sets. For example, the data set that I showed you earlier, the DL4TO data set. You have access, you can build, train, and evaluate all types of deep learning methods for the different approaches that I showed you earlier, and 3D visualizations. All the visualizations here are from this library. This is, for example, an illustration of the SIMP method, of the iterative nature. This QR code leads you to the site with the full documentation and with the tutorials. But I will also show it at the end again. Okay, next I will show you some of the experiments that I conducted with this library. In this paper, which I mentioned earlier, the DL4TO paper, I learned a mapping which takes as input a problem, and as output we obtain the final optimized density. And the first thing that we need to answer is, how do we pre-process the data? The most trivial way would be to simply use all these tensors that we have available, like the forces, the Dirichlet conditions, and so on, and just concatenate them into a tensor and put that as input into our network and then get the output, right? That would be the easiest way. And this is why I call this pre-processing the trivial pre-processing. We just concatenate all the information that we have. However, one of the big problems that I find with with the current state of the literature in this field, is that most researchers simply solve this problem as an image-to-image segmentation problem. So they don't take into account the physics, the underlying physics. And that's something that I tried to improve. So my first step was that I used a different type of preprocessing, which I call PDE preprocessing, where I used the full block, basically, and solve the PDE on that. And the idea is that from that you already get some idea of the load paths. I don't know if you can see that on the slide here, but you get some physical information into the model of the load paths that the deep learning or that the model takes. And usually I concatenate these two, but I will show some experiments later for that. Another property that I used in order to enforce physical correctness in a way is group equivariance. We had already had some talks on equivariance yesterday. If you can look at the definition, but I think it's very easy to understand if you look at this image what equivariance means. It means that if you rotate the input, like if here you have a force from the right, and then you rotate this by 90 degrees and you get a force from the bottom left, then you would expect a physically correct equivariant model to, if you apply it to this one, you get this solution, and if you rotate the input, you would expect that the output rotates too, accordingly. So that's what equivariance means in this setting. Physical correct models do that, but deep learning models not necessarily have this property. So that is something that I tried to enforce. If I have some time in the end, maybe I can talk about how I enforce it. I do this via group averaging. And the nice thing is that you can choose any type of group that you want. In this case, what makes sense is to use 90-degree rotations and to use mirrorings. And this is just one of the plots that I show in this paper, where you can see that the message of this plot is that if you use physical information into your deep learning pipeline, if you include it in your deep learning pipeline, you need less training samples. So you can see here the different types of preprocessing that I use. This is the trivial preprocessing, and this is trivial plus the PDE preprocessing. So we add some physical information. And then I have without and with equivariance. And you can see here predictions of models trained on different numbers of training samples for the same sample, outputs for the same sample. This is the ground truth sample. And you can see that when trained on 1,500 samples, all of them work fine. But this model here really needs these 1,500 samples to give any good outputs. Whereas this model, which has access to equivariance and PDE preprocessing, already comes up with quite good results after only 50 training samples. And in this paper, I conducted a lot of experiments like that, not only for individual samples. Yes. So to sum up, I published a deep learning for topology optimization library called DL4TO, which you can use and which is entirely built on PyTorch. And you can use it for classical methods as well as deep learning methods. I also have this paper here in which I conducted a lot of the experiments that I did using this library. And I have these data sets. Yeah, that's my talk. Here's again the QR code if you're interested in the documentation.
Okay, thank you very much for the nice talk. Is there any question for David? Yes.
Yeah, thanks for the great talk. I was wondering, when modeling these shapes, basically use like an occupancy function, or like a density function, I guess you said.
Yes.
Do you enforce sort of the shape connectivity somehow, so that the shape doesn't scatter into lots of disjoint points?
No, that's not directly enforced, but it's indirectly promoted, let's say, because if you okay, we can talk about, you mean the deep learning model or you mean the classical method?
The deep learning model, the last one.
Yeah, in the deep learning model, it's also not included, no. But since we have the ground truth which are connected, obviously we hope that our model outputs a solution that looks similar, but it's not directly included, and this is something that can happen. Yeah.
Okay. So you experienced that also during testing, that sometimes you have scattered shapes.
Yes, that happens sometimes. I try to measure that phenomenon by using two metrics, basically. So the two metrics that I use to evaluate my shapes are the IOU. I took the IOU and compared that to the ground truth, and I checked if the model prediction fails. If I use a classical PD solver and calculate if it fails or not. So these are the two metrics that I use. So if the material is scattered in a way that the structure fails, then yeah, this metric detects it. But otherwise, not, no.
Okay, thank you. I think there was some.
The pictures look like you use the Cartesian lattice. I was wondering about metrication artifacts and if they can be reduced if you move to face or body-centered cubic lattices.
Sorry, the library. You mean what with the library that I use for the plotting?
So the spatial discretization. Do you operate on the Cartesian lattice?
What I do is I operate on the centers of the voxels.
Mm-hmm.
So and what I then do here is I smooth the vision for visualization purposes.
Mm-hmm. But the voxels themselves are from a Cartesian lattice.
Yes.
Yeah. Okay.
Yeah.
And so other lattices like the face and the body-centered cubic, they're a bit more isotropic than the Cartesian. And I was wondering if that could have advantages.
I didn't do any experiments on that specifically. No,
thanks.
I don't know. But
very interesting talk, by the way.
Yeah,
thank you.
Thank you.
Okay, there's time for another question. Yes.
So thanks for the great talk. So I was wondering, you already said that there's one downside to deep learning would be that you have to collect a lot of data and pre-compute with the classical method. What do you think could reinforcement learning help with that, in the sense that you could have an agent that's sort of step-by-step optimizes the topology, and in the end you could, let's say, once estimate the compliance and then treat it as a reward?
Yeah, maybe that would be an idea. I didn't look into that, and I didn't read any research papers who had this idea. But
yeah, a colleague, I can send you something.
Okay, nice. Yeah, yeah. Unfortunately, I can't really evaluate if this is a good idea or not. But yeah.
But thank you.
But I can say that unsupervised methods usually don't work well for this.
Okay, let's thank David again. And now it's the turn of Håkon.